All right, we've got our one last technique that we're going to learn. And before we learn the general rule, I just want to motivate it with an example. So my question is, how many distinct arrangements of the letters in the word mom are there? So M-O-M. Well, one is to leave them as they are, right? Leave it as M-O-M. Another option, if we just think about it, well, we could do M followed by M followed by O, or we could put the O first, which then makes it M second. And if we think about what we're doing and thinking about all the different options, this is it. These are the only distinct options because those M's are identical. So we have three different ways. Now, if we think about our other counting techniques, well, this one really would not be a combination because we're not picking groups of things. We are arranging things. There is a first thing, second thing, third thing. The problem is the things are not all distinguishable from one another. They're not all different types of letters. So if we had tried sequential counting, sequential counting principle would say, well, I'd have to arrange the first thing, second thing, third thing. There's 3 letters for the first option, 2 for the second, and 1 for the last. It would find 6, which is too many. And the problem is, it is counting the 2 M's as different, right? It would count something like M1, O, M2 as different from M2, O, M1, right? If I flip the 2 M's, it would think that it's different when really it's not because they're identical to one another. So this new scenario that we're in is we're talking about how do we arrange a set of things where not all of the things are distinct, where some of the things are identical. So in a set of n total objects where there's different types of objects. So there's some number, say R1 of type 1, there's some other number R2 of type 2, so on and so forth, RK of type K. So there's different types of letters or objects or things. And then there's certain number of each of that type. And the idea is the things in these types are not distinguishable. There's no way to tell them apart from one another. Then the total number of distinct arrangements of the n objects, we're going to have a formula for it. And it turns out the formula looks like n factorial. So remember, n is the total, divided by, in the bottom we're going to put the factorials of all of the quantities of the different types. So I'll have R1 factorial times R2 factorial times, we'll just keep going until I run out of types, RK factorial. So this is the number of things in each type. And we'll finish out that division. So in our simple little example there, so in the mom example, well, our types would be the 2 different types of letters. So in total, I have 3 letters. As a part of that, there are M's, of which I have 2, and there are O's, of which I have 1. So in total, what we would do then is n factorial, which is 3 factorial, divided by the factorials of the different types. So divided by 2 factorial times 1 factorial. So then that would be 3 times 2 times 1 divided by 2 times 1 times 1 factorial is just 1. So in the top, 3 times 2 times 1 is 6. In the bottom, 2 times 1 times 1 is 2. 6 divided by 2 is indeed 3, which was the number that we found when we just counted the ways. So what you have to do in this one is recognize that there's different types of objects, that they're not all distinct, And if we want to find the total arrangements, then we find, well, how many total objects do I have, and then how many of each different type do I have. So we've got 2 more examples of this that we're going to try on your worksheet.